Aiman bin Amir. My ID number is 20001156.
Hello, my name is Chia Sue Siew, 2100-2023.
Hi, my name is Nur Syuhaida binti Muhamad Ridzuan and my ID number is 20001093.
Hello, my name is Christopher Ku Vun Tsung and my ID is 20001102.
This is the introduction. In our integrated design project, these are the conditions given. Then we choose anthracite as our fuel and its heating value is this. These are the processes in each of the components of the steam power plant. These are the formula that can be used for calculation. Our project is based on Rankine cycle, and the deviation between the Rankine cycle and the actual is represented by isentropic efficiency. The isentropic efficiency formula are these two, and then the backward ratio is this.
This is our proposed plan of a steam power station which is operated based on Rankine cycle. We will use water as the working fluid since it can be get easily from the sea. Firstly, we have a boiler. It is used to heat up the water into a superheated vapor before it goes into the turbines. The heat is supplied by the combustion of coal at the furnace into the boiler. Plus, thermodynamic process that involved at the boiler is isobaric heat addition. Next, we will use 5 turbines. All of them are arranged in parallel, so each of the turbine will have the same condition and proportion of the steam. The turbine will generate power with the isentropic efficiency of 98.5%. The thermodynamic process that involved here is isentropic expansion. Then, we have a condenser with R134A as the cooling medium. Here, the heat from working fluid will be removed to the cooling medium by condensation process. Due to the phase change from vapor to liquid, there is no temperature change of the water. This condition is really important when we are going to design the condenser. The thermodynamic process that involved here is isobaric heat rejection. Lastly, we require a pump. The pump will use some power produced by the turbines. Here, the pressure will increase as well as the temperature back to the initial condition. However, it operates with isentropic efficiency of 96.5%. The thermodynamic process involved at this pump is isentropic expansion. At the end, the process will keep going in a cycle manner.
Now, we are going to discuss the proposed solution. The calculation will be based on the ideal condition. We are given the condition at the inlet of the turbine string 1 which is at 7 degrees Celsius and 30 megapascal. From the given data, we do the calculation by a reverse calculation to get the properties of each string and then the work net out which is 220 megapascal of electricity. These are the 4 thermodynamic processes and 2 assumptions involved. At string 1, given temperature 973 Kelvin exceeds the critical point of temperature. This shows that string 1 is superheated vapor. The values below are the properties of superheated vapor. At string 4, at the boiler, the pressure will remain constant. We assume the temperature is at 120 degrees Celsius. Since the pressure at string 2 is greater than the saturation pressure, then string 4 is in compressed liquid. From table A7, we got the properties of compressed liquid. At string 3, based on the Rankine cycle, string 3 is a saturated liquid. Since 3 and 4 are isentropic processes, their entropy values are the same. We can calculate H, T, and P values by using linear interpolation. At string 2, since string 2 and 1 are isentropic processes having the same entropy value, from table A4, using linear interpolation to calculate these values. Based on the Rankine cycle, string 2 is a saturated liquid vapor mixture. By using this formula to determine the quality S value and calculate the H2 value using this formula. This is a summary table of the properties at each string.
Next, we will calculate the amount of heat transfer. At boiler, the heat is transferred into the system. condenser, the heat is transferred out of the system. Now, we will calculate the amount of work. At the turbine, the work will be produced. Meanwhile, at the pump, the work will be consumed. Work net out is equal to work produced at turbine minus work consumed at pump. The thermal efficiency is the ratio between work net out and Q in. In the next part, we will summarize the collected data. First part is the amount of coal required. The coal chosen is anthracite with enthalpy value of 30,080 kJ per kilogram. By knowing the amount for Q in, the mass flow rate can be obtained, which is 19.26 kg per second. For 1 day operation, the amount of coal required is 16,640 and 64 kilograms. For back work ratio, which is equivalent to pump and turbine work, the value is around 0.025. The overall efficiency is 38.6%. The actual power produced differs from Rankine cycle due to irreversibilities. By knowing the isentropic efficiency for both turbine and pump, we can calculate the actual power produced. Next, for the number of equipment, only 1 unit is required for generator, pump, and condenser. However, 5 units are required for turbine in order to produce 220 MW of power. For the amount of steam generated, it can be obtained by multiplying the mass flow rate with the specific volume at stream 1.
In conclusion, in our proposed data, we have the power produced by the turbine, the inlet of the turbine, the temperature and the pressure, the source of fuel and its amount, and the amount of steam generated. This is the number of each of the components of the steam power plant and the overall efficiency, and our steam power plant is in Rankine cycle. For recommendation, we have 2 recommendations to increase thermal efficiency. However, all the conditions need to be considered for safety and cost. Thank you.